冤家，我就想问你一个问题啊，就是最近的课听得懂吗？听得懂？哦，看你有时候没有有点心不在焉啊？你在什么？什么？看前面？哦，看前面的内容呀。如果听不懂的话，要问啊。就看到有时候你好像啊消失了啊，状况一下啊，啊每天过年呗。哦，对对。Hey, you guys learn construction on number natural number before? Never? Huh? So, I mean, could be done in discrete math. So when we define 0, 1, 2, 3, 4, 5, right? So how we define it? So we start with an empty set. Okay, here is an empty set. And then we define, wait, let me think. So 1 we define as an empty set. So don't have 0. Okay. And 2 we have uh empty set of empty set. Let me think. Oh, we have this. Learn this thing or not? Let me recall. Let me write down what am I thinking first. So I have 0, 1. Wait, so you guys never see this before? Most of you don't. So define wait, let me check something. Okay. So I mean, we start with empty set. Okay. Empty set is zero, right? Nothing inside there. Okay. We call this zero. Okay. And then what's one? We call a set containing an empty set. Okay. So there's an element in the empty set, which is the empty set. Okay. Set of empty set. So we can count one. And at the same time, this is zero. This is equal to zero plus. Plus is a successive function. Okay. Plus one. So we can do one plus 1 is 2. Okay. 2 plus 1 is 3. Okay. And then what happened to 2? How we define 2? We define 2 using 1 and 0. Okay. So 0 is an empty set, and then 1 is a set of empty set. And then we continue this construction. So you include everything before. Yeah. So this is the one of the construction of natural number. So you start with empty set. Okay. 1 is a set of empty set using this operation here. This is a plus operation actually. Successive operation. Okay. Previous set union with set of the previous set. And then you can continue this. Okay. So that's why I put this meme here. So imagine the empty set is a burger with nothing. And then you can add a nothing burger. And then keep going. This is the meme for the construction of natural number. Why? Huh? Why I tell some joke also blur? Teaching also blur. Huh? Hungry. Hungry. Alright. Yes, okay. I'll try again. Hey, Pigeon, where are you last week? Overslept. Okay. Wednesday and Friday, both there. Oh shit. Okay. Okay, it's okay. Yeah. I was wondering what happened to you. Okay. Any question on assignment or lecture or project or presentation? Any question or not? So next week, I made announcement again. So we start at 1 o'clock. We start at 1 o'clock. And then if we can finish earlier, then we finish earlier. If not, the latest is before your ODE, right? 6 o'clock. Okay. Yeah. Hopefully we'll finish by 5. Maybe some, not sure, but maybe some of the AIT students will come. You also can invite your friend as well if you want. Yeah. Invite your friend. Yeah. Father can invite your father. Or your father want to join online or not? Teams. Okay. Yeah. So yeah, at that time maybe I need someone to be my timekeeper. Yeah, timekeeper. Okay. So that don't go over time too much. Yeah, so during the presentation, everyone can ask questions. Okay, up to 1.5 minutes. So the one get asked right. Okay. I don't really care how accurate your answer is, but I care about your response. Okay, this is like an interview. Okay, when you go to a job interview, maybe you don't give the right answer or accurate answer, but they see how you react to the answer. Okay, so better don't stand there stand still. Okay, so you need to be responsive. Okay, yeah, use your uh, first, first what? First, first, huh? Intuition. Okay, you can use your intuition to answer. Okay, the thing you think you are right. Yeah. So what for 5 minutes actually is it or between time or not? Yeah, yeah. You on the spot. Yeah, on the spot. On the spot. You answer. Then too much already. Too much. I mean, your boss won't work for you. And there's still a lot of people coming for interview. Okay. I mean, reality is like this. Okay, this is reality. Okay, it's not me. This is reality. So this is reality. When you go to job interview, they are like, for example, Tesla. Okay, Tesla come to Malaysia. Okay, they say only 5 positions. 3,000 people go and interview. Do you think you have so much time to wait for a person to think on? 3,000 people go for interview for 5 positions. Right? Okay. Make sense or not? Yep. Question time plus presentation time, 1.5, 1.5, total about 3 minutes. But we expect maybe we will like go a bit longer, but yeah. I finish earlier. Don't drag too long. Yeah. About 5 minutes each person, maybe longest. Yeah. Yeah. If very interesting, maybe we will go longer a bit, but we don't try to make it boring. Yeah, so okay, regarding the topics, right? The latest you give me a topic is without discussing with me or not, is next Monday because I need to come up with a schedule also. Yeah, I need to come up with a schedule with your topic. Okay, by next Monday, everyone should give me a topic already. Whether you already discussed or you haven't discussed with me. Okay, by next Monday. What else you need to deal with? Anything else? Yeah, you can. You can. Yeah, but don't just read the paper, right? You can bring some prompt for you yourself. Sure. But don't just yeah. So I mean it's a proper presentation skill. Okay. Don't just stare at the screen or stare at the mm. I don't really care about the the dressing, but if you like, you can wear formal. Yeah. Up to you. I mean, the culture here is wear formal, then you wear formal. But if you don't wear formal, I won't penalize you. At least now. Yeah. Okay. Maybe in future, yes, I'm not sure. But yeah. Because what? Yeah, I mean, yeah, I don't know the same. Yeah. Any other question? Are you guys clear what you need to do already? Okay. Okay. So I mean we only have 3 more weeks left. So we will finish up vector calculus and then go for the exam. And then go for exam. I already told you I'm not around at exam week already or not? I'm not around exam week, but you can still message me, but maybe a bit slower responding. Yeah. So during the exam day, so you can ask Darren questions. So he will like help answering the question. Mm. Yeah. Okay. Okay. Yeah. So our our syllabus is a bit distorted. Yeah, distorted. Because what I'm going to introduce later, actually, we have been using it, okay, which is the vector function. So let's go through vector function really quick, okay, before we go into vector calculus. So you can think of vector calculus is the calculus on linear algebra. Okay, calculus on linear algebra. We no longer deal with one variable, we deal with more than one variable. Okay, so before that, uh, can you recall what kind of function you have seen before? Example of function. Periodic. Okay, good, very good. So at the start, we spent 3 weeks on series. Okay, series. So series, for example, Fourier series, power series, what are these functions? These functions are going from where to where? From where to where? You just have an input x, and then you match around with this x, and then get another number. Okay, so you have function from R to R. Okay, so for example, power series, Fourier series. Okay, and then before series, you play around with sequence, right? Okay, so what are sequence? Sequence are function from natural number to real number. So A1, you give me a real number. A2, you give me a real number. A3, you give me a real number. Okay, so these are sequence. How about next? Else, series, test. All those are for integral tests, for convergence of what? Convergence of series. Okay, convergence of series. Yeah, still in series. Okay, what sort of object you have seen? Parametric equation. Yes, good, very good. Parametric equation. So parametric equation. The example we see, we just up to R2, is it? Yeah. Okay. So this is what we're going to see today. Okay, from R to Rn. Okay, this is what we're going to see today. R to Rn. So maybe I think the highest we will care about is R3 because you can only draw R3 things. Okay, R to R3. So give you a time. You give me a vector in the space. Then you tell me where you are, given the time, just the time. Then give me any, and tell me where you are in the 3D space. Okay. Yeah. Okay. So this is our main topic today. So this is what we call a vector value function. Okay. Vector functions is the vector value function where the domain is a set of real numbers, and then what you get is a set of vector. Okay, in general, R to Rn. Give you a number, give me a vector. Okay, live in Rn. Okay, so in next case, we call it R actually. So let's call it R. Okay, so you have a time t. Okay, time t gets sent to a RT. Okay, sometimes we'll put a hat to denote this is a vector. Okay, so uh, how to specify a vector function? Okay, to specify a vector function, you need to tell me every component. What's the function? Okay, tell me every component. So there are n component here. Okay, in this case, we take n equals to 3. Okay, we have 3 components here. You need to tell me what happened to every component. Okay? So in general, we can write this function as, for example, ft, gt, and ht. Okay, so these vectors change according to my time. Change according to my time. Okay. Okay, so you can put it as a column vector or row vector. Okay. Maybe in calculus you will see more row vector instead of column vector, but it's the same thing you see in linear algebra actually. Okay, just different convention, row or column vector. Okay. So okay. Okay. So vector function, you need to tell me every component what function you use. Okay. Okay, for example, this R is a function from where to where, Yuanjia? Yeah, this function here, okay, this R is a function from where to where? Huh? From what space to what space? What's the domain? How many input you need? Huh? T. How many input you need? Sorry? 3 input? I mean, here is the input. How many input you need? 1. Okay, so it's what space? Sorry? 1. R or R3? R, okay? So your input is R. Output, okay, how to read this? Do you know how to read this? IJK, what is IJK? IJK are the unique vectors, okay, in R3, okay? In other words, we also can write this function as the row vector, okay, t cubed, comma, ln 3 minus t, comma, square root t, okay? Also, if you like, I like column vector, t cubed, ln 3 minus t, square root t, okay? So these are equivalent way of writing it. Okay, so what's the call domain now? R3. Okay, so it's R3. All right. So you need to check. Okay, you need to check. Is it everything in R satisfied by this? Can fit into this function or not? Is this R the natural domain or not? Huh? No. Why? Any restriction? Okay. What happened to ln 3 and square root t? Okay, you only define ln is defined on 3 minus t is greater than 0. Okay, how about square root t? Okay, also is defined on t greater or equal to 0. Okay, so let's see which restriction will make some changes. So 3 t is less than 3, and then 3 have to greater or equal to 0. Okay, so these two conditions fix your domain. Okay, because t cube is defined everywhere, right? Polynomial equation, polynomial function. Okay, so these two conditions fix your domain. So what's your domain here? So your domain is actually something in R. What's your domain here? What's your domain here? Okay, so t smaller than 3, but t greater or equal to 0. So in other words, we can write it as interval. Okay, how to write it as an interval? So from negative infinity to 3, but not including 3, correct or not? Okay, union with 0, but we can include 0 to infinity. Okay, make sense? Where? Intersection. Why intersection? Okay, wait. Oh, I thought it's negative. Yeah, so intersection. Yeah. So, okay, so actually we can rewrite this one. Yeah, we can rewrite this one. In this way, we can rewrite this. Yeah. Okay, so I mean, actually to see this, right, maybe it's better to draw this up. So you got everything less than 3, okay, and then everything greater than 0. Okay, so what you have is in between 0 and 3. So in this case here, we can further reduce this to 3 and 0, including 0. Increase 0 to 3, correct? Okay. Okay. Yeah. Okay, good. Yep. Yeah. Okay, next. So, so how to take limit of a vector function? Okay. So you just take at every component. Okay, you just take at every component. You just check limit at every component. So let's do this example here. Okay. So how to take limit of this function when t go to 0? Okay. So you take limit at a vector function, you just bring the limit into every component. Okay. So this is the definition. You just bring limit to every component. Okay. So what's the limit you get when you take t equals 0 for the I part? Okay, good. So 1 times I. How about the j part? A j part? 0. Why? Why is it 0? How to compute t to the e minus t and then taking limit? How do you compute this? Huh? L'Hopital. Do you need L'Hopital or not? How to take limit of a quotient or a product? Huh? Huh? 0 over 1, right? So the denominator go to 1, okay? The numerator go to 0, okay? So the denominator is non-zero. So both of them are continuous, so you can just, since limit exists, so you just bring the limit to top and bottom, okay? So you get 0 over 1. So it's 0. 0 over 1, which is 0. Okay, how about the last one? Sin, wait, stop. Huh? J, okay, sorry. Yeah, how about last one? Sin t over t. L'Hopital. Okay, so this is a very classic one. So sin t over t close to 0, they are the same. Okay, close to 0, they are the same. Otherwise, you can use L'Hopital to solve this. So this is just 1 times k. Okay, by L'Hopital. Okay, so very simple. So far. Okay, so how is it continuous? Similarly, you want every point to add. So when a vector function is continuous at A, you want the limit to be equal to the function taking at that point. Okay, the value of that function taking at A. Okay, is similar, but you need to check for every component now. Okay, previously you only check for one component or two components. Now you need to check for every component Rn. Okay, makes sense. Okay. Okay, so this is what we call a space curve. Okay, so this vector space is what we call a space curve. So let's say our F, G, H are continuous. Okay, then the curve traced out by this function is called a space curve. Okay. You know why this function, the R to Rn, always give a space curve or not? Why is it not a surface or other thing? Why is it a curve? Just curve. You know why? You know why you can't draw a surface or something like that? Why is it just curve? I mean, a function, okay, a function R from R to R3, okay? So R is equals RT is defined to be FT, GT, HT, where all of them are continuous. Okay, why you only get curve, not surface or something like that? Yeah, it is similar. So why? Yeah, it's similar. Yep. So why? What was the similarity between these two? Uh, almost, not quite, almost. Because you only have one R, you only want to have one input R. Okay? If it's continuous, you only can join this dot together. You cannot form two linearly independent vector or lines. Okay? For example, the previous chapter, what do we learn? Previous chapter. Let's go back here a little bit. Previous chapter, what do we learn? That's what I said, a bit distorted our syllabus here. So we are going from R2 to R. Okay, this is what we did. Okay, this define a surface using graph. Okay, yeah. Okay, so our domain is only have one t. Okay, only have one variable to play around. Okay, give you a time, you give me a dot. Give me a time, give me a dot. Okay, but in previous chapter, we can change the xy component. Okay, we fix x and then we go y direction. Fix y, go x direction. And then all in the middle, we still have points. Okay, so we form a surface or plane. Okay, bended plane. Okay. Okay, so really depend on what's your domain. Okay, if my domain change to R3, for example, the triple integral. Okay, we change to R3. So what happened? What's the graph doing? Huh? So the graph out R3 objects in R4. Okay, if you look at the graph. Okay. Is it okay? So core domain. So the core domain, the domain determine the objects you draw, the graph you have. I mean, type of object you will have. Make sense or not? So if I have map from line from R is a line. Okay, so it tells you how this line sit inside the graph. Okay. Yeah. So if I have a function from R to R3, it tells you how this line sit inside R3. So let me draw something. Okay, so you should imagine this basic shape. Okay, so for example, R, you should imagine as a real line. R2, you should imagine as a plane, infinitely plane. So if I have map from R to R3, it tells me how this line sit inside R3 if it is continuous. Okay, let's see inside R3. And then what? And then this. Okay, and then this. Okay, so what's R2 to R? Okay, last time. So if we look at the graph of F, okay, it tells me how the plane sit inside R3. Okay, so graph of F. Graph of F. Graph of F. Maybe you might ask, hey, why not this is a R4, right? This graph shouldn't live in R4. Shouldn't this graph live in R4? Okay, but we hide the time variable inside the curve. We hide the time variable inside the curve. So I will give you the orientation of the curve, and then you follow that orientation. That's the dimension of my time. Make sense or not? Okay, so we only draw this R3 space. Okay, we only draw this R3 space. So the R here is hiding inside my curve. So I tell you the orientation. Make sense or not? Makes sense. Okay, later maybe we'll see more example, then you will see it. Okay. Yeah. Okay, so you can see that this picture here. Okay, this is a generic picture for a vector function in R3. Okay, so every time you have a vector, but remember time have orientation. So from past to future, for example. Okay, so past to future like this. Yeah. Okay, so yeah, you can see that this is a general uh, function for a vector space. And do we have more picture? So let's try this. Describe the curve. Okay, describe the curve defined by the vector function below. So how to describe this curve here? Any idea or not? This one actually looks similar to something you every time you guys solve in linear algebra. And can you see it? Maybe you make it into a vector column form, maybe it's easier to see. 1 plus t, 2 plus 5t, minus 1 plus 6t. Still not familiar? Okay, so let's split further because this is a vector. Okay, so I split into this form here. Yeah, what's this? Okay, yeah. So does this look familiar or not? What's it? What does it look like in linear algebra? A line, okay? Solution to the homogeneous solution, right? Homogeneous equation, sorry. Okay, so it's a line. Okay, so this is the line. So what's this direction of this line? Okay, so the direction is 156. Okay, passing through a point 1, 2, minus 1. Okay, so this is a line. So this is a line passes a line that passes through 2 minus 1 and parallel to 156. Okay, yeah. So this is just a degree 1 polynomial. How about next one? This one. How about this function here? Cos ti sine tj tk. What does ij direction here satisfy? Circle, okay, circle equation. If because cos square t plus sine square t is 1. Okay, but when you go around the circle, this t, right, increase in the z direction. Okay, in the z direction. So you should imagine that this is a circle, and then when you go around the circle, you go upward a bit and then keep going up. Okay, so it is spiraling around the unit cylinder. Okay, spiraling around the unit cylinder. Okay, so this is the we call a circular helix. Okay, so okay, maybe I don't write. Later I will add the notes in. So you can see that this xy here, so satisfy circle, unique circle in particular equation. Okay, and then increasing in t. Okay, increasing in that z direction. Yeah. Okay. Next, find a vector equation and parametric equation for the line that join these two. Okay. I think we didn't touch on vector equation and line parametric equation in this class. Okay, let me show you. Okay. So what do we mean by vector equation and parametric equation? So how to make out a line? Okay. To make out a line, you need 2 points. Okay. So 2 points are given here, P and Q. So to make out a line, what's the ingredient you need to have? What's the line formula? Have you seen before? So the line formula is a point plus the direction times t, which is what we have just now. Okay, so this is the general formula. So you need a point, you need a direction vector. Okay, so what's the point here? What's the point you want to take here? Okay, so the point I want to take here is 1, 3, minus 2. Okay, and the direction I'm going to take here is, you can see that this is a line from P to Q. Okay, so I'm going to take P to Q. Okay, I'm going to take P to Q. So what is PQ in this case? Simple. What's PQ? 2 minus 4, 5. Yes, I believe you can do this. So how to do this? How to compute this? PQ. What's the formula you use? What minus what? Yeah. Q minus by P. Okay, so not just Q, we call the vector all Q and all P. Okay, so all Q minus all P. So you take your terminal point minus your initial point. But how you remember this? I think this is not how I remember it. I will do it as PO plus OQ. Okay, PO plus OQ, because it's a direct resultant vector. Okay, but all PO equals to minus OP. Okay, so that's why. Yeah, that's why I got this formula here. If you want to remember this formula, you can think of, you take the terminal point minus the initial point. Okay, so there are some subtlety here. There are some subtlety here. You see, this is a point form. This is a vector form. Okay, so are they equivalent or not? Are they equivalent? Point and vector. No? No? Okay. So given you a point, what's the point does? What does the point does? The point give you a coordinate. Okay. Coordinate you count from origin. Okay. So I give you a point coordinate. Actually, you get a vector from the origin to that point. Okay. So given a coordinate, you will get a vector. Okay. Okay. So the vector is a vector from the origin. Okay, this is very important. Vector from the origin, because I'm going to show you what is 1 minus 4, 5. Where is this line here? You have to draw minus 5 minus 1 minus 4, 5. Where is it? So 1 maybe somewhere here. This is also 1, so maybe draw here as a 1. And minus 4 on this direction, 5. Okay, so you can see 1 minus 4, 5 doesn't represent this line, right? Okay, doesn't represent this line. So we need to shift it. Okay, how do we shift it? We shift it by this P point here. Okay, so that we can get this line. Make sense or not? Does it make sense? You see, PQ, this vector here is somewhere away, somewhere along here. Okay, so this is a PQ. But this is not the line we want. We need to shift this line by P. We can shift this vector by P. Make sense or not? Okay. Okay. Okay, I mean, if you don't understand, you really have to ask. Okay. Okay, so good. So can I change to Q or not? Can I change this point to Q? Can I change to Q or not? Yes. Okay, you still get the same line, but your starting and ending point change. Okay, because our time is given a orientation, maybe 0 to 1 in this case. Okay, we fix it 0 to 1. If you put it as Q, where do you start? You start at Q instead. Okay, but our direction is going from P to Q. Okay, does it make sense or not? Okay, so this line here, right, is a line with orientation. It's not just a line. Because y equals to mx plus c, right, can be any line. Okay, but there's no direction here. But here, when we put the t in, this t here, this control the orientation. Okay. Okay. So in principle, if you just look at this line here, you also can swap this direction. Go to the other side, also can. Okay, if you just care about line. But if you care about line segment, then you need to take care which direction you go and then where you start, where you end. Yeah. Is it clear? Okay, understand. Okay. Okay, good. So what's the vector equation here? Okay. So vector equation is the vector sorry, wait. So vector equation here, we write it as the vector function. Okay. So to write a vector function, you need to tell me function at every component. Okay, component factor. What's the function in every component? Okay, first component, what do we have? Ellie, what do we have for our first component? What's the function for this line? I? Function. Don't know? So this is the line equation. Okay, how you get the component function up? I plus t. This is not I, or this is 1. 1. Okay, 1 plus t. Okay, good. How about a second one? Second component function? 3 minus 4t. Okay, good. And then, okay, good. So you need to be able to swap between these notation, row and column. You need to be able to swap, and then also ijk. Okay, so these are all equivalent way to write it out. And then the domain is from 0 to 1. Okay, the domain is from 0 to 1. Okay, another way to write it is called the parametric. Okay, so what do we mean by parametric equation? So in parametric equation, right, you need to tell me every coordinate, what rules do I follow? Okay, for example, here we have x, y, z. So what rule do I need to follow for x, y, z? Okay, how about forgot the name. Who is beside Yan Po again? Wei Zhe. Oh, that one is Yi Zhou. Okay, Wei Zhe. Okay, Wei Zhe. What's x? What's the rule x have to follow? My x component of this graph is to follow what rules? Huh? This line here, the x component need to follow what rules? 1 plus t. Okay, good. How about y? Okay. Ah, okay, good. Z? Z plus 5t. Okay. Yeah. Okay. Yeah. So when I ask you question, for example, this presentation, this project, right? So actually, I'm preparing you for final year project. Okay. Because when I was marking or grading their final project, right, I also listened to their presentation. I feel like what did you do in your yes? Okay. I mean, yeah. So I mean, I'm trying to get you to expose to this kind of environment. Okay. Otherwise, you just graduate like that. Like that. You know what I mean by like that? Yeah. Okay. So now is the way. Now is the give you the chance to practice yourself. Okay. Yeah. All right. Okay. So this is the this is that. Mm, how about we? Yeah. Question. Yeah. Do I get a zero? Okay. Where do I get a zero? T from 0 to 1. Right. Okay. Good. So um there's some pre-assumption I made here. Okay. So the pre-assumption I made here is the place I start with is 0. The place I end is 1. Okay. Then you need to check whether this is true or not. Yeah. Then you need to check whether this is true or not. This is a general formula, but you can check that actually this give you that line. This formula give you the line. Okay. So when you plug, so what do I mean that by that? So when you plug t equals 0, you will get p. Okay. When you plug t equals to 1, you will get q. Okay. Yeah. So this interval here, right, really can change. Okay. When you change this interval, what do you mean by that? Actually, you reparameterize it. Okay, you reparameterize. Reparameterize. Do you know parameterize? Parametric equation. So you parameterize that formula. Okay, maybe you use t divided by 2 or 2t pi t, something like that. Yeah. Okay. Reparameterize. Okay. So let me so reparameterize. So if you use different interval, that means you reparameterize it. Okay. So what you need to measure is the starting point is P and the ending point is Q for the line segment. Depend on what's the direction you have. Okay. Mm. Uh, Then you need to put in the last point is 2, right? Okay. So do you compute to Q or not? No. You if you made it T over 2, then yeah. Yeah. So yeah. So what have you changed? What have you changed? Okay. You don't change the line, but you change the speed. You change the speed. Okay, you change the speed inside this curve here. Yeah, you change the speed. You don't change the line, but you change the speed. Okay. So I think you have come across this arc length reparameterization, right? Forgot already. I think calculus one heard before. Arc length parameterization. Arc length. Don't know. Forgot. Don't know. No one remember this? Arc length parameterization. Arc length reparameterization. No, forgot. Okay, I mean, that one is to reparameterize so that your speed is always constant 1. Yeah, if not, never mind. I mean, maybe later we'll see it or not. Okay, so maybe I not very important, so I skip the example. This one, I will post up the solution. Okay, let's get into something else first before we break. Okay, let me see. Maybe later we'll see a little bit on reparameterization. Okay, so once you do limit, right? Okay, you should expect something already. Limit, continuity, differentiability. Okay, this all comes in a package. Okay, they come in a package. Once you have limit, you can do continuity. Once you have continuity, limit, you can do. Actually, you just need limit to do differentiation, differentiability. Of course, it has to be continuous first. Okay, so what's derivative? Remember what's derivative or not? You take the limit of the secant. Okay, you take the limit of the secant. Okay, do you guys imagine what I'm trying to say? So let me go back. Okay, so let's say you want to take limit at the point P. Okay, at the point P, or this RT here. Okay, at the point P. So you know that this is the line that touches this curve at one point, right? So how do you know how slanted you want. Okay. So this is very precise. The construction is very precise. So how do you construct it? So you take a nearby point. Okay, you take a nearby point, and then you form this is what we call a secant. Okay, so you form a straight line from P to the nearby point. Okay, and then you do it for every nearby point. Okay, you do it for every nearby point. Okay, until you take the limit, the nearby point is just the P itself. Okay, so you will get, in the end, you will get this tangent line here. Okay, of course, you can see this is the right of the curve, right of the point, but you also can take left of the point. So there are two-way limits. Okay, they are different way. Okay, so but these have to agree. Okay, they have to agree. No matter how you take the limit, they have to agree so that this differential exists. Okay, so this is why you guys look at this RT plus H minus RT. This is the secant line. Okay, you look at that point and then look at the point nearby. Okay, divided by H. Why divided by H? Remember when we find the gradient for one variable function, what do? Y2 over y1, y2 minus y1 over x2 minus x1. So you divide by the change of x. Okay, so here also divide by change of x. Okay. Okay, so this is a generalization. So everything you do right is a generalization from easy cases. Okay, from easy cases. Okay, so you need to keep in mind this construction. Okay, so you can see here is a secant. Okay, you take limit of the secant and then you will reach this tangent vector here. Okay, tangent vector. Okay, so what's the difference between this and the previous definition? What's this? What's the difference here? What's the difference of this derivative with the previous definition? You saw a few type definition of derivative already, right? So what's the difference here? This is produced by a vector function. Okay, so when you study the limit here, is a difference of vector function here. Okay, difference of vector function, and then you take limit of vector function. How do you take limit of vector function? Just now I already say. Yeah, you just take it component wise. So you do it component wise. Yeah. Okay. Yeah, you do it component wise. Okay, good. All right. Okay, you do it components wise. Okay, RT is the tangent vector to the curve defined by R at point P. So there's an easy theorem here. You don't need to go into the epsilon delta stuff. So if you want, you have a vector function. You want to differentiate your vector function. How to differentiate? You just differentiate components wise. Okay, same. Okay, components wise. Very important. So how to look at vector function? You just look at it component wise. Okay, this is the key concept. Look at it component wise. Okay. So unit tangent vector is just tangent vector divided by the length. Okay. Next. Okay, let's do this and then we will take a break. Okay, let's do this and then we'll take a break. So what's the derivative of a vector function? What's the derivative? How to take derivative? Components wise. Okay, so key concept here, component wise. Okay, apply every operation component wise. Okay, so when you differentiate the first component function, what do you get? Raise 3t squared. Good. How about second one? How about what do you get if you differentiate the second one? Second component function. Can you see? You get You know what am I asking? Find the derivative of the second component function. You don't know how to do that? Huh? You don't know how to say in English. This is t. This is the exponent function. E what? Minus t. Okay, e to the minus t, and then plus t times. Okay, minus t times what? E to the what? Minus t. Yeah. Okay. Yeah. I mean basic mathematical term you still need to learn. Okay. So how about differentiating sine 2t? You just get 2 cos 2t. Okay, so this is the derivative. Uh, how to find the unique tangent vector at the point where t equals 0? Okay, so you can see that this is not quite vector, right? This is the vector function r prime t. Okay, it tells you every t what's the vector, every t what's the vector. Okay, so the next question is when t equals 0, what's the unique tangent vector? Okay, so first you need to get the tangent vector at t equals 0 first, which is 0 plus e to the 0 minus 0 plus e 2 times cos 0. Okay, so all together we get j plus 2k. Okay, or if you like, this is a vector 0, 1, 2. Okay, correct? Yeah. Okay, so this is the vector. So at that point, you have this tangent vector. So how to get unique tangent vector? You just divide by the length. Okay, so this is the normalization, okay, in linear algebra. Okay, so what's the unit vector here? So what's the length here? Theta, what's the length here? Square root of, so 1 square plus 2 square. So 1 over square root 5 times 0. Okay, so you can see that here asks you to find the unique tangent vector. It's like when we want to do the derivative, direction derivative, right? We need to have the unique direction vector. Okay. Yeah. Okay, so far any question before we take a break? Hopefully in 2 hours time we'll finish this lecture, this chapter, and then we will go into vector calculus. I mean this chapter is short. Sorry? Or vector calculus is the last chapter. Yeah, vector calculus is the last chapter. Yes, we finally come to an end. Yeah. Okay. Yeah. So we take a break first, and then we come back till 3:15.
Jacobian 啊，Jacobian 就是跟我们的那个 Jacobian 是一样的吧？什么是 G 先？要看 G，Jacobian of 这个东西嘛，所以 G 是谁？G 呢？对啊，我要看 G。对，你看这里，他这里介绍了 JG is the Jacobian determinant of G 是这个，所以你看一下它跟 G 什么关系？你看这个 G 是什么？G 是一个 R2去 R2的 map，OK？、所以呀，你看这是一个 vector，哎，sorry，就我知道这是什么哪的？没有，这是 definition 罢了。对，就是这个 definition。Jacobian of determinant of G 是这个，所以你要 differentiate 你的那个那个 core domain 的 variable，用你的这个 domain 的 variable，对吗？我们在考虑。我们怎么学哈？哦，就是你没有来那天。哎，没有，我们学过了，只是我们那天是做练习。就是当我们在讲那个 one to one transformation 的时候，比如说rectangular coordinate 转去 polar coordinate，或者rectangular coordinate 转去 spherical 跟邻居哥说，你记得吗？不是有一个 r d theta r square sin phi d r d theta 那些那个多余的那个东西是 Jacobian 算出来的。然后怎么算那个 Jacobian 呢？就是用那个 transformation，也是跟这个一模一样，就是它 transformation，给我给你看，是我刚刚 post 的，不知道有没有写，我看一下，因为我没有在 summary 里面写。呀，你看，看一下有没有 OK，我可能写一个最难的 OK，因为这个可以 apply，所以你看啊，我有一个 transformation 从这个去到这个，你的这个是 G 等于 G 级了，你就有这两个吧，OK，所以怎么做呢？你要把所有的那个那个 codomain 的 variable，OK，differentiate partial differentiate with respect to 它的 domain 的 variable，yeah，这就是一个单纯的 definition。它是一个 definition，对，没有没有，我以为它是为什么印特好的时候会用？它就是 change of variable，它就是 change of variable。你看它是 change of variable，对，它是 change of variable。你看这个，你看感觉放在这边比较正常一点，因为我们这个放的地方也是变的地方，所以它跟变的一起这样子讲啊。呀，但是可能他对这个有兴趣，还是他已经知道这两个，所以他这样子翻。他是换了一下那个什么，因为你对是要求 x、y 的 probability，求 UV 的 probability 是吗？求 UV 对吗？Destiny 啊？求 x、y 的。求 UV 对，求 UV。对，求 UV，因为他会把已知的东西全部放在这边，通常。它就是这个就是个 transform，对，一个 transformation，对对，因为他们之后是不是要 integrate 这个东西？他们肯定是之后要 integrate 这个东西。你看，如果 integrate 这个东西啊，这东西可以丢过来。呀，因为呀，被发推吗？这东西。不是，它是 definition 来的。哦，知道你的意思是说，为什么 chain variable 这个东西会跑出来吗？对，这个东西我没有解释，但是我有把它 attach 在这里。它是这个原因，我可以大概跟你讲，如果你要了。我没有解释，但是我有把它放在 note 里面，如果要读的话。但是它的原因就是这个，你的想法是这样，因为你在 XY 的 coordinate 它是一个正常的 rectangle，OK，但是你 change 了 coordinate 过后，这个 rectangle 可能它被 ban 了，ban 了过后你就不知道怎么算它的 area，因为它不直嘛。但是你可以把它 unban 回来，怎么 unban 回来？就是透过这个 Jacobian。透过这个结构边把它 unbend 回来，你就可以知道它的长度跟它的厚度。然后它怎么 unbend 回来呢？需要透过这些 derivative 来算。That's why 这个 derivative 跑出来，就是因为你在把它，就是刚才一样啦， 就是它越来越靠近，越来越靠近，越来越靠近，然后它就 form 了这两条线，然后用这两条线来算它的 error，然后这两条线算出来的东西就是这个结构呀。嗯，你要知道的话，你要看这三个 slide，为什么这个结构边会跑出来是？
记得我之前有问过这个题
啊，
我之前有问那个 R 什么
啊，对，就是这个出来啊，怎么出来？就是你去算这个结构边，它就出来了。然后至于为什么要算这个结构边，是因为你看本来是 band 的三角形，四方那个 rectangle，然后你可以 unband 它变成这个青色的，但是你 unband 过后呢，你的边呢就被这个 factor 增加了这个 factor，对
我不去看。
呀，你再看一下。
我又在做其他东西。
做其他东西，做东西，CS 几十讲。Hey, I got one video to show you. Maybe you will feel related. Always start. Huh? No. Why you want to see that? Okay, can relay. Yeah. Yeah, so you guys start off from April, May, June, July. Okay. Yeah. Yeah, but I mean, uni time is really quick. Like for me, like 8 years also passed like quite so fast. Yeah. So it's really quick. So do appreciate your uni time. Yeah. Okay. Yeah, we will skip a few examples here, right? So because this chapter is not the key chapter we want to spend time on, we just want to use the tool inside this chapter. Okay. So in particular, we skip this example. I will provide solution. You can study it. Okay. So more important is what kind of operation we can take inside this vector functions. So let's say we have two vector functions. Okay. So you can see that mathematics is like this. So you define one things. You want to think whether how I combine two of them. Okay, how I combine two of them. Let's say we have two differentiable vector value function. Okay, u and v, and f is a differentiable real value function. What does it mean? F is a function from where to where? Okay, so u and v is a function from r to, okay, rn. If you want, you can generalize to rn, but we just keep it at r3 now for our class. F is a real value function. What does it mean? Where's the codomains lie? Value in r. So the value is in r. So the function, the value of this function is in r. So the codomain is r. Okay, real value is r. Vector value. So this function give me a vector. You give me an input, I give you a vector. Okay, so this is the meaning of vector value, real value. Okay, so, and then C is a scalar. Okay, C is a scalar. You know that scalar, you can think of it as a function also. Yeah, it's a constant function from R to R. Okay, sometimes it's useful to think like that. Okay, so if you differentiate the addition or difference of two functions, you can just differentiate individually and then add them out or take the difference, because differential is a what kind of operator? Differential is a linear operator. Okay, good, very good. So in particular, if you differentiate a scalar multiply a vector value function, you can just take the scalar out and then differentiate. And then how about you multiply with a real value function? Okay, you still do the usual product rule. Okay, you still do the usual product rule. But when you differentiate on a vector function, how do you differentiate? How to differentiate a vector function? Michelle, how to differentiate a vector function? Vector value function, yeah. Huh? Only in the past hour. Well, how to differentiate a vector value function? Huh? What's the key principle here? Huh? Sorry? Okay, so you differentiate component wise. Okay, because you define vector function also component wise. Okay, differentiate component wise. Okay, how about you differentiate a dot product? Can you do dot product on vector value function or not? You just do dot product on at every point. Okay, so what do you think? Okay, actually you also have product rule. Okay, you also have product rule, but not that what you get here. You dot two things together and then add another product of dot product. What do you get? Huh? You get a number. Okay, so this is a thing live in R. Okay, or function of R if it is T. Okay, function of R. Yeah, I think right like this is okay. Okay, this is a core domain. How about here? Here is a thing live in Rn, okay, or R3. Here is also R3. Here is also R3. Okay, okay. Okay, how about cross product? If you cross two vectors together, what do you get? You get another vector. Okay, so you get another vector. So how to differentiate cross product? You also use product rule. Okay, also use product rule. So these are very good. So they stay the same. Okay, how about differentiate of composite of vector value function and a real value function? Okay, what you do is also you use the chain rule. Okay, you also use chain rule. Okay, you also use chain rule. Am I misleading if I use this notation here? I feel like a bit misleading. So this means the core domain is in R3. And core domain is R3, core domain is in R, core domain is in R3, core domain is in R3. Is it misleading? Misleading or not? Okay, I know what to do. Okay, let me skip this. Okay, so this is a function from R to R3, R to R3, R to R3. Here is R to R. Okay, here is R to R3. Here is R to R3. Okay, yeah. So this one I tell you what are these function is. Okay, so in principle you should prove all of these. Okay, in principle you should prove them. Okay, how do you prove them? Do I want to show? When I say you need to prove them, do you know what you need to do or not? Do you know what you need to do? You don't know. Okay, this is the problem. If you know how to do, then I can let you do. But so what you need to do? So you need to apply the definition. Okay, apply a definition. So what to do? Let's pick one of them, and then we try to see what we need to do to prove one of them. Okay, let's say put this. Okay, let's say we prove this. Okay, prove the second one. Proof of 2. Okay, proof of 2. So so UT. So you need to write out the form of UT first. Okay, write out the form of UT. Okay, because we only know how to differentiate component by component. We don't want to go into the limit definition, right? We just use the normal property. Okay, so write down what is UT. Okay, let UT to be a function from R to R3. So how to define a function from R to R3? Tanya. IJK, okay? Components wise, components wise, okay? Define it component wise. So call it FT, GT, and HT, okay? Yeah, for since they are differentiable, right? So they are all differentiable, F, G, and H, okay? So you define it to be in this form. Now we can play around with this function already, okay? So the left-hand side, so you need to start with left-hand side and then prove the right-hand side, right? Okay, so left-hand side is what? So it's differentiating. How about I move all of these in? Okay, so differentiating C times UT, okay? So what is UT in this case? Okay, this UT is defined components-wise. So maybe I keep my row column. I like row column. Column vector, I mean, sorry. Okay, so what's this? C times a vector is equal to what? This is a vector operation. So you can bring the C to every function. Okay, so you can bring the C to every function. So you get CF, CG, CH. Okay, so how about Xie Mei? How I differentiate this vector function? How to do differentiation on vector function? Two words, one word actually. Component wise, okay, do it component wise, okay? So you differentiate component wise. So differentiate dt cft, okay, and then d over dt cgt, and then d over dt cht. Okay, so how to do this? This go to a one variable function differentiation already. So what happened to the derivative? It's also linear on the on function of first one variable. Okay, so you got this. Also, okay, so there's something to do in each step, right? So this step is by definition. Remember what I said? If you don't write reason, most of the case you are wrong. Okay, so how about second step? Second step here is the vector scalar multiplication. Okay, how about the third step here? This is the linearity on linearity on function of one variable. Okay, so you're applying linearity of the differential operator on function of one variable. Okay, we rely on this fact here. Okay, and the definition of vector function because you do it components wise. Okay, okay. So the key here is you use the linearity on function of one variable, something from calculus 1. Okay. Okay, so from here, is it clear what you need to do here? Is it clear or not? You need to bring the C out again. So you do the reverse vector scalar multiplication. Okay, so you bring the C out, C of everything. Okay, so this is a reverse. Okay, maybe I write on the other side. This is C times d over dt ft, and then d over dt gt, d over dt ht. Okay, so this is just a vector scalar multiplication again. So what's this large vector here? Guli, what's the vector? What's the vector shown here? C times what vector? What's this vector? You differentiate component wise. So what do you get? You differentiate components wise. Okay, these are component of what vector? What function? Ft, gt, ht is component of what vectors? Vector function, I mean. What's the assumption? What's the assumption here? These are the component function for ut. Okay, so if you differentiate it components wise, what do you get? Ut. You already differentiate components wise. What do you get? Yeah. So you differentiate ut components wise. So what do you get? So the logic definition logic is going forward. Now it's coming backward. Okay, so backward is what? How you differentiate ut? You differentiate components wise. Now I already differentiate components wise. What do I get? Yeah, different derivative of ut. Okay, so I get derivative of ut. Okay, yeah, I get derivative of ut. Okay, which is c times u prime t. Is it okay? Okay, okay, yeah. So going forward, backward. So definition is really if and only if, but normally we just phrase it as if something happened. Yeah, because that's the thing you need to check. Okay. Yeah. Okay. Yeah. So I skipped this example here. I think you can calculate it. I will show you the answer later. But maybe we do this proof question real quick. So show that if the length of my vector function is a constant, then r prime t is perpendicular to rt for all t. Okay. Can you think of one example why is this true? Huh? Can you think of why is this true? If my length of my space curve is constant, why my tangent vector must be perpendicular to my vector? Can you think of one example or not? Can you think of one example? Zero vector. Okay. So last time in our class, right, always we say sometimes we ignore the trivial example, but trivial example is still important. But there's some non-trivial example here. One can figure out. Okay. Yeah. So can you figure out? Okay. So one example is the circle. Okay. So let me write down what we have. So suppose the length of RT is a constant. Okay. Want to show what? So we want to show that R prime T is perpendicular to RT. Okay, for all T. So one example is a circle. Okay, you can take unit circle. Okay, you can take a unit circle. And actually you can check that. If you take a point here, okay, and then you draw a tangent vector here, it is always perpendicular. Okay, this is what this this statement trying to say. Okay. So why is it true? Why is this true? Okay, why is this true? So let's see how to prove it. This question here, right, is really an example of direct proof. Okay, so we start with what we have, and then we will end up with what we want. Okay, so we need to end up with what we want. So to show that it is perpendicular, that is to show that the dot product is always 0. Okay, so what do we have? Okay, we start with what? So we start with this line here. Okay, the length is always constant. What's the definition of the length? Definition of length. Square root of what? Square root of the dot product of the vector. Okay, dot with itself. Okay, so in this case here, I will write RT dot RT is equal to C squared. Okay, yeah. So you see, you got this, and then you got the other one, the other dot product you need to get to. So what's the difference between these two? One of them have derivative, right? The other don't have. And then one of them you get 0, the other you get a constant square. Okay, so how do you bring in the derivative? How do you bring in the derivative? Jimbo, how do you bring in the derivative? Jimbo, how do you bring in the derivative? Oh, what operator you need? Differentiate. Differentiate. Okay, differentiate both sides. Okay, you differentiate both sides with respect to t. So you differentiate both sides with respect to t. Okay, so you differentiate both sides with respect to t. So how you differentiate a dot product? Product rule. Okay, good, very good. Just now we say differentiate a dot product. Differentiate what? What? The sound, huh? Differentiate. The multiplication. What? Huh? On the screen. On the screen. Okay. Yeah. So differentiate the dot product. You also use the product rule. So R prime T dot T
plus r t dot r prime t. Okay. On the left hand side, right hand side, what do you get? You get 0. Okay, you get 0. So you see, here I'm not thinking of it as a constant anymore. I think of it as a constant function. Okay. So you see, these two are equal as number, but when I differentiate, I see it as a constant function. Okay. Okay. So what do I get here? So I get 2 times r prime t. Yeah, 2 times r prime t dot. Sorry. Yeah. Wait. So okay. Yeah. 2 times r prime t dot with r t equals 0, which means that r prime t dot equals to 0. Okay. Yeah. Yeah. Okay. Hey, do you guys know why this last step here is implied the number inside 0? Why? Can you see why? So, oh, okay. Yeah, sure. Yeah, sure. Yeah. Okay. I mean, what I want to say is maybe in general, this is not true. Okay. If you have something non-trivial multiplied to 2 to be 0, then this could be something else. But in the real number, it has to be 0. Okay. Yeah. If you change to different number, then number field, then you will have different thing. This is a property of real number. Okay. Yeah. So okay, so this is general. Okay, this is general. So you can extend it to multi-dimension. Okay, 2-dimensional, 3-dimensional, 4-dimensional sphere, 5-dimensional sphere, n sphere. Okay, you can consider n sphere. Okay, in particular, you also can draw a sphere, 3D sphere. Okay, and then you can draw the tangent line. This tangent line is always perpendicular to the position vector of your point on the sphere. Okay, yeah, okay, good. I got a question for this. Okay, quite straightforward. Okay, okay. So next is integral. Okay, so similar idea, integral. How do you integrate integral? Integrate a vector function. You also integrate component wise. Okay, you can integrate component wise. Skip example. Skip example. Okay, produce component wise. Okay, yeah. So here, since you haven't touched on arc length, so maybe you talk a little bit of arc length here. So what's the length of a space curve? Okay, so the length of space curve is defined by this integral here. So it's the integral of square root of dx dt squared d plus dy dt squared plus dz dt squared, which is the length of my tangent vector. Okay, which is the length of the tangent vector. So why is this a square root square coming out? Do you recall what the Pythagoras theorem is? Okay, so Pythagoras theorem is c squared plus a squared. C squared equals to a squared plus b squared, where a and b are the side of the right angle triangle and c is the hypotenuse. Okay, so in this case here, how you measure c? C is just square root a squared plus b squared. Okay, so you can see that here the a and b here become a small change in the x direction, small change in the y direction, small change in the z direction. Okay, and then you do this Pythagoras theorem in a higher dimensional. Make sense or not? Okay, and then why do we do this integral here? Why do we do this integral here? Because our curve is not always straight. Okay, so we need to take the secant smaller and smaller and smaller. Okay, so that's why we introduce this integrals here. Okay, so for example, just now here, okay, this is the limit, kind of limit we take. Okay, this is the limit we take in the integral. Okay, so there's a limit. So when you see integral signs, right, integral represent what? Limit and sum. Okay, limit and sum of lines. These lines getting shorter and shorter and shorter and shorter. So this sequence getting shorter and shorter, shorter and shorter until you can approximate the whole line. Okay, so now, so you see, if I divide the times up, okay, further and further, I can approximate this line better. Does it make sense? When I split out the time, and then I can draw the secant again, draw the secant again, draw the secant again. Okay, yeah. So this integral represents the process of taking the time interval to infinity, okay, until you reach every line here. Then you form the whole line. Does it make sense? Okay. How about do one exercise? Okay, maybe do one exercise. How about maybe we don't do this one. I prove to you how useful is it. So let's do the other one. So no, don't do this. So let's do this. So RT of cos Ti and sine Tj. Okay, just do two variable is enough. Okay, what's this graph? Okay, when I tell you this vector function, right? I should tell you the domain, where the domains lies. Okay, if I don't tell you, that means I take everything, the natural domain. I'm gonna fix it from t from 0 to 2 pi. Okay. Yeah. So can you compute what's the arc length, the length of the curve that I put here? You know what this curve is? Any idea? Isham. Circle of radius. What's the radius? 1. Okay. Center at 0. Okay. So this is the parametric curve from what is this? 1, 0. Okay. And then a circle go over, come back at 1, 0. Okay. So this is the direction. Excellent. Yeah. So try and compute this. So in the lower dimension, okay, what's the formula? You don't need the z direction anymore. There's no change in z. Okay, so you need to compute this dy dt squared dt. Okay. So your a and b is 0 to 2 pi. Square root of dx dt is y is what? dx dt. dx dt is what? Okay, negative sine t squared plus dy dt is cos t. So altogether you get you get 1. Okay, differentiate, integrate 1 over 0 to 2 pi. You get? Okay, you get 2 pi. So what's the circumference of 2 pi r? Is 2 pi. Okay, so this represents the arc length. Yeah. Okay, so this example here, right? Okay, this example, there's one interesting part of this example is you can see that this is actually is this circle here. You cut it and then you bring it up. Okay, but in general, when you bring this rubber band up, okay, actually it should shrink in. It shouldn't come to the same point again because you travel more, right? Okay, so if you compute this example, right, you can see at this point coming back to the same point as 1, 0. So this means that this rubber band gets stretched. Okay, so you get a longer length than 2 pi in this case. Okay, if you go back and compute it, it is 2 pi times square root 2. Okay, yeah. Okay, yeah. Yeah, so you can think of this as you cut the unit circle, and then you bring it up to different height for the other endpoint. Okay, yeah, sure. Okay, continue. You want to do velocity and acceleration? Okay, I briefly mention about it. Okay, maybe we don't do exercise. We just briefly mention about it. Okay, so why we do differentiation? Why we do differentiation? Okay, because the motivation is in. Hey, actually, you guys, I'm quite curious and skeptical. Are you guys reading my Moodle page? You guys follow my Moodle page? No, you only download and then upload stuff. Follow your YouTube. Okay, sure, good. I mean, you also have to read the Moodle page. Okay, you should read the Moodle page. I give you a clear guideline how you use my material there. Okay, the pre-read, tutorial, review question, lectures, how I do it every week. You should read it. Okay, I write so long, not for fun one. Okay, you should read it. Okay, yeah. So anyway, but already almost finished the semester. So you should read the Moodle page, and then I forgot what I want to say. Okay, yeah. There's one question I put at the top. Who knows? There's a one question I put at the top of my Moodle page. Anyone know? Yes. Okay. So it's calculus invented by Newton or Leibniz. Okay. So the motivation they built this topic here is exactly because of this velocity and acceleration. Okay. They want to compute the. I don't know about Leibniz, but Newton want to compute the orbit of Mercury. Yeah. And also other orbit. Yeah. Okay. So they want to compute what's the derivative, how fast they move. Okay, how fast they move. Okay, and yeah. So there's a rival between these two. So I don't know which one of them invented first. So I mean they in old times, right? It's like conference. They talk to each other. So maybe I tell you, you got this idea, I also got this idea, and then you go back and work it out, I go back and work it out, and then we both work out together. Something like that. Okay? Yeah. Okay, it's like that. Okay. So yeah, so the main motivation is this velocity. So if you differentiate once, you get velocity. Differentiate twice, you get acceleration. Okay, F equals to ma acceleration. And then of course, the main motivation here is the things in R3. Okay, so maybe this is the place that started. Okay, in R3. Okay, yeah. These I can provide this solution, but let's see if anything important. Yeah, so Newton's second law of motion, F equals to ma. Okay, so you're given a vector function. How do you find acceleration? You just differentiate twice. Okay, differentiate once, you get velocity, and then differentiate twice, you get acceleration. Okay, yeah. And then this is the projectile. I will share this projectile here. Okay, hey, maybe I talk about this projectile. Okay, there's a very interesting route we take in AI last time when we discuss this question. So this projectile is, you have a projectile, okay, shoot from the origin, okay, from the angle, with a positive axis with initial velocity v0, okay. Assuming the air resistance is negligible, the only external force is due to gravity, okay. Find the position function RT of the projectile and what value of alpha maximize the range of T. You know what's this question asking? So it asks you which direction, which angle you throw, okay, you will get a maximized D. Okay? So this is a typical question, typical problem you will meet when you play sports, right? Yeah, you play sports. For example, you throw basketball, Or you throw what kind of ball? Badminton, you don't throw. Okay, also, yeah, very important. You hit which direction you hit. Okay, which one is the furthest? Okay, and what kind? Of futsal also you take you use
American football.
American football.
Water
Okay. What? Water rocket? What's water rocket? Water rocket? Never heard of it. What water? Huh? Football? Oh, okay. It's like shoot the coke, like they put in coke or metals, not that one. Or just okay, yeah. And maybe also, yeah. Okay, good. So yeah, so which angle we throw, then we will get the maximized range. Okay, last time we come up with this weird solution. We said that as long as the top point is the furthest, then the okay. So let me point out. So last time we ended up compute where this is the longest. Okay, and then somehow this will determine the longest D. Yeah. So this is what we did in the AI last time. So let me show you. In my other class. Let me show you this one. Sure. Wait, let me find where is it. Wait, let me find first. Okay, here. Yeah. If you like, you can read about it later. I'll put it up. Yeah. We ended up compute where is the highest. Where's the furthest point for the highest point in the projectile? Okay. The maximum distance for the highest point in the projectile. Somehow this will determine where's the furthest D. Yeah. Okay. So there are two methods here. So you can go through this method, first method, and then we go through the second method here. So the idea is we thought that this will compute the largest point. Actually, we compute the wrong point, but somehow this will give us the furthest angle. Yeah. Yeah. So the problem here is the equivalent formulation is these two, the furthest distance of these 2 points, okay, the end point and the highest point will determine this angle. Yeah, you can read about this. I will share it out later. Okay, yeah, so we done with this. Okay, so actually there's one more thing here. Actually, there's a very interesting here. So the angle we found is 45 degree. Okay, so you throw 45 degree, you will get the highest, longest distance. But between 0 between 45 and 45 between 90, there's a symmetry then. Okay, there's a symmetry. So you see, if you less than 45 here, and then maybe you above 45 with the same difference, they will throw to the same point, but with different height. Okay, so so this optimal point is kind of intriguing. Very intriguing because once you throw to the optimal angle, you will get the furthest angle, but away from this optimal angle, right, you will get less, and they are kind of symmetry. But of course, this one is based on air resistance is negligible. Okay, but if in real life, right, the air resistance at the bottom is higher than the top. If the bottom is higher than the top, because when you get higher, there's less air. Okay. Yeah. So this is a perfect condition where you don't need to consider other forces other than gravity. And then it is symmetric. Okay, so you can see that a lot of imagined situation, right? Perfect situation is there's a lot of symmetry.
Okay, but in the real life, there will be different condition, different answer. But still, we can still find symmetry. In physics, they will call it something like broken symmetry. Yeah, broken symmetry. Okay. 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 Yeah. Okay, you can read about this. I will post it up. Not too important. The important stuff is vector calculus, how to do calculus on vector function. Because we are going to vector calculus now. Okay. Oh, I take another break. Yeah, another break until 4:07.
走了。是一小问题，最后想进去。我
但要警示。要写什么？我发这么多个哎。或者真的把它简单化。把它约减嘛？对啊，还是你需要它这么出来？你们去反正方选的还是反正什么方式？啊，那你最后要减。这个就是哪个？报告而已啊，OK。我做
完全抽卡的一个，
抽卡。
一个抽卡的一个。
就是全部化。好，哦，OK，我知道，OK，OK。好，一个我给包的，没有吧？也可以。那我们一个第四个，能玩吗？你能玩吗？我问老板，我们现在有3个问题了。打工同学玩，你说他知道还最强。但是我觉得可以，因为这个课不是你赢在另外一个班是2个时间进去，所以你但是我们因为我们也不做外国课的，会把我 spend 多时间的地方，就是 derivative 的那一课，其他就要算就可以了。呀，
同学上的他专门讲1分啊
你讲45度是最
啊，
现在你算咯，
你现在是要正他为什么？
为什么要45度？呀，现在要正为什么是45度？我看啊，你要找它这条线，
记得这种，
同学上过的，
对，上过的就不太需要，也不太需要考个人的，但是反而复习。
我看一下啊，为什么我们要考这个逻辑啊？因为我把它拆成，我把它拆成 x 跟 y，把它拆成 x 和 y。
对，
我们不是只看那个 s square 的 shape 啊，我们排成 x 和 y，所以 x 有一个 direction，
increase 哦，
然后 y 有一个这种 parabola，
对，它会上升。
所以 x 跟 y 可以表达成这个东西。应该首先是要先找这个先，找了这个过后，才开始 maximize。
你 split 的，
但是这个 maximize condition 其实很少了，就是你要 make sure 它 end 在这边就可以了。你 end 在这边过后，你就可以看到你的 alpha 要拿多大。呀，其实没有什么 choice 的，其实你只要make sure 它停在那边，然后你就没有什么 choice 了。然后那个 choice 就是5度。但是非常有趣的是这个，刚才我讲的这个，我们那时候做错，因为最大嘛，全部最大，你要找 maximum point 就赶紧找一个来 differentiate 一下，等于0下找个 critical point 这样子做，这样子做一下，somehow 啊 angle 是对的哦，然后就觉得很奇怪，所以其实说是什么呢？你这个点呢，已经 determine 了你之后会发生什么事情。如果你这边要远，这个也要远，这个远，这个也远，它是 symmetric 的。
可是不可以太远，你有个度的，你丢太高就
没有，我不会，这个就是我刚才提的这个东西，这个就是我提的这个东西，就是你太高啊，反而它又短， 它不会去到远的，
对啊对啊对啊
所以你这个远最远跟这个最远是一样的。
对对对，一起的，
啊，是
一起来的，一起来
啊，
的，
是一起啊，对啊，
对啊对啊
对啊，就很神奇啊，就是你是 determined by，所以你一出呀啊，或者说就是你一出去就 determine，但是问题这个就是跟这个 graph 有关系了，跟这个 graph 有关系，其实呀，这样子啊，呀，很
我 get 不到，
你 get 不到
有趣。
有趣哈，get 不到什么有趣啊？就是一开始我们以为算错了嘛，因为算的是 critical point 最远的地方嘛。但是 in the end 那个 critical 最远的话，就是也可以证明了，其实你可以 travel 最远，因为不一定永远是对的嘛，这个东西，这东西不一定是永远对。如果换科的话就不一定对，对不对？但是问题是这个情况是对的。Yeah. Okay, we will start soon. We'll start soon. Okay, we'll start soon. Please be ready. Okay. Huh? Ready or not? Ready? Not yet? Go. Wait. What? Okay. Okay, so we'll learn about vector calculus. Okay, vector calculus. So what's the possibility that we haven't touched before? Okay, we have function from R to Rn. Okay, and we also have R3 to R, for example. What kind of possibility we haven't touched yet? What kind of possibility we haven't touched yet? Maybe R2 to R also. What kind of possibility we haven't touched yet? R infinity. Okay, maybe we can go in between different m and n. Okay, we can go between m and n. Okay, we go between m and n. Okay, so actually you saw this before. Okay, but you didn't realize. Okay, you showed this. You saw this before. So when have you saw this? Gradient of f. What's gradient of f? Okay, gradient of f. What do you get? You get a vector function. Okay, but this vector function here depend on 2 points, x and y. Okay, so this is a function from R2 to R2. Okay, so vector function is a function from R2 to R2. Let's say we take f from this space here. So maybe we pick a name for it, G. Okay, so actually you encounter this. So this topic is about studying these things. So these are what we call a vector field. Okay, physics name. So vector fields on R2. Okay, so we have a set D, a plane region. A vector field R2 is a function that assigns each point xy in D a two-dimensional vector fxy. Okay, so I give you a point xy.
okay, and then give you a vector at that point, okay, at x1. Similarly, you can do it on R3, okay, give you a point on R3 and then give you a R3 vector, okay, vector field on R3. So a vector field is what? It's a function, okay? So if you heard physics people telling you vector field, vector field, vector field, vector field, it is a function, okay? Function from where to where, okay? If it is on R2, it is function from R2 to R2. If it is on R3, then it's a function from R3 to R3. Okay? Makes sense? Okay. So if people tell you a vector field, vector field, vector field, so in mathematically terms, it's just a function. Okay? Function from the space to itself. Okay. Give you a point on that space and then give me back a vector. Okay. Let's look at one example here. So there's a vector field on R2. Okay. So when we say about vector field, I need a function. Okay. On R2, meaning this function is from R2 to R2. So can you check that whether this function is from R2 to R2 or not? Okay. So if you give me a point, okay, I give you a vector. Okay, ij minus yj plus xj. Okay. So do you have this table with you? Can you guys spend some time and compute this? I compute this. Yeah, try compute this table here. Try compute this. Okay, after you compute, right, try and draw the picture out. Okay, over this point, you draw a vector. Over this point, you draw some vector. Vector field, I think, is a kind of hot topic in mathematics research, but it's at the same time very hard. Yeah, vector. No, I know. But you can study and then we can collaborate. Yeah. Okay, so what vector you get? Anyone finish compute? Huh? You got something? 0, 1, negative 2, 2, 0, 3, 0. Okay. Okay. Negative 3, 0. Which one? Negative 2, negative 2. Okay. Or the other column. If you already finished compute, right, try and plot the graph out. Try to plot the graph. Over the point, draw this vector with the direction. How about the second column? Syed, do you have it? Do you have second column answer? Don't have? Uh, Yongzi, you do have? Yeah, Yongzi, yeah, do you have second column? Okay. 1 0. Yeah, 1 0. 2 2. 3 0. Okay. So you can put this point up. Okay. In particular, you can look about. Okay, let me group some term together. 1 0 minus 1 0 0 1 and 0 minus 1. Okay, let's look at this. These are the point on the unit circle. Okay, so what can you see here? You can see that the length here is 1. Okay, the length of the vector here is 1. Over other points, the vector are longer. Okay, they are longer. Okay, so over this point, what do you have? In the 1 0, you have 0 1 direction. Okay. And then if you follow the circle, what's the next coordinate? Is 0 1. Okay. So here you got the upward direction on 0 1 0. Okay, let me use this color. On 0 1 direction, you have minus 1 0 direction. Okay. What's the next point? So you have 1 0 here, 0 1. Okay, minus 0. Okay, good. Minus 1 0. What's the direction? 0 minus 1. So this direction is going downward. 0 minus 1, correct? So going downward. How about 0 minus 1 at the point 0 minus 1? Is the point 1 0. 1 0 is the horizontal line or horizontal vector. Okay, so it's this. Okay, on this circle, it looks like this. And then you can try and plot the other point up. Okay, and what you can see is this diagram here. Okay, so this represents the vector field. So if you put a particle here, right? Okay, this particle will following the direction of your arrow. Okay, this is what we call vector field. Okay, okay. So if you put a particle here, this particle will fall with this arrow here. Okay, because why we study this vector field? Because these usually come from a gradient, gradient of a f. Okay, so you can follow the direction, right? Okay. Remember last time I talked about a slanted plane. Okay, so the gradient is going downward. So when you stand on here, right, you will naturally feel you want to go downward. Okay, so this is the vector field. This is what the vector field means. Okay. Yeah. Okay. Oh yeah, sure. Yeah. Yeah, sure. You mean you write j minus 2i 2j? Is it? Yeah, sure. Yeah, these are all equivalent formulation. Okay, so something to note here. Here we put point. Here we put vector. Okay, point and vector. So these are the points that we need to evaluate at. Then we get a vector. Is it okay? Okay. So you need to differentiate between points, vector. Sometimes point is vector, but depend on what you want to use, where you use it. Okay, where you use it. Okay. Okay. So some other example is this. This is a upward pointing vector field. Okay, which is given by this. So x divided by the length. Okay, x divided by the length of the vector, and then y divided by the length of the vector. So altogether, what do you get? Actually, you get the unit vector. Yeah. Okay. So you can see that these lines are almost the same length. Okay, it's almost the same length because you use the unit length 1 at every point. Okay. What can you do? Next is you can change the sign here. Okay. If you change the sign here, everything will point into the origin. Okay. If you change the sign of y. So if you change the sign of y, then it points into origin. And in particular, so let me see. So for example here, okay, let's look at G. Call it another G. Okay, minus x over square root x squared plus y squared I minus y over square root x squared plus y squared j. Okay, so if I multiply minus, so what happened to the vector if you multiply a minus? Change direction. Okay, this one very important. You put a negative, change the direction. Okay, throughout this chapter, very important. So in this case here, since it's pointing outward, right? So if you take minus, it point inwards. Okay, point inwards. So what kind of thing that point inwards? So one thing you can consider is the gravity. Okay, Newton law of gravity. Gravitational force field. Okay, so this is the equation for it. Have you guys seen this in your physics or not? GMN over R cube. Yeah. This is a Newton law of gravity. Okay. So yeah, so you heard about what's the term? What's the term? Universal gravity, is it? And gravity. You know? Universal gravity and gravity. So there are gravity inside our Earth and then gravity between two objects. Okay. Yeah. So this gravity here apply to most of the objects, but it fails to explain the orbit of Mercury. Okay. So there's some flaw in this theory here. That's why Einstein come up with this relativity. Okay, where gravity is no longer a force. Gravity is a result of geometry. Okay, gravity is a result of geometry, a curved geometry. Okay, so because it is curved, then everything when you flow with the curve, for example, the basing. So why you design like that? Okay, because when the water flow, it will flow down automatically. This is what gravity doing. So gravity, it sink the space around it. So when you stand on this space, you will automatically fall into the bottom of the sink. Okay. Yeah. Okay. So next, gradient of a scalar field. Okay, it's gradient of a scalar field. So what's a scalar field? So a scalar field is a function from Rn or R3 to R. Okay, scalar. So the value of this function is a scalar. Okay, that's why we call a scalar field. Field is a function, right? Okay. Now we say scalar field because the value of the field is a scalar. Okay, which is real number. And suppose this function is differentiable, and the gradient of f is already defined before, which is if it is two variable, we just take del f, del x on the x component, del f, del y on the j component. In three variable, we will do extra del f, del z. Okay. So after you take the gradient, these are the vector field. Okay. So you obtain vector field from scalar field. Yeah. Okay. So let's see this. Find the gradient vector field of a fxy equals to x squared y minus y cubed. What function is this? This function takes in how many values? Two values. Okay, so this is a function from R2 to Venus. From R2 to where? To R. Okay, right. Because we just take multiplication, take power operation, and then take difference. So you just get R. Okay. Yeah, you get R. So this is a scalar field. Okay. So how to obtain the gradient vector field? Let me see. Forgot the name. Seng. So how to obtain the gradient vector field? Huh? 2x. Yeah, I mean, what's the definition of gradient vector field? Sorry? I mean, no, I mean, you need to, okay. This is a real case, real case. In the FYP, right? Okay, the student present the code. Okay, I say, please explain what you did in the code. Okay, no, I say, how do you solve this question? Okay, some question. And then she scroll through the code and then show me on the screen. And then we start for about 1 minute. So I mean, you can't just say, I give you this. Okay, go and read this. Then what for you are here? You know what I mean? So you need to explain to people. You need to explain to people why is this true. Okay, what is done in the code. Okay, why this code will help to answer this question. Okay, yeah. So I asked how to find the gradient vector field. Okay, so you can answer like, what's the gradient vector field? What is it? What's the definition of gradient vector field? What thing you need to do? You need to take the derivative. Okay, what derivative you need to take? First derivative of f with respect to different direction. Okay, and then you take the sum. Okay, so how was the gradient vector field? So we compute del f. Okay, so what's del f? So in the first component, you need to do del f del x. Second component, you do del f del y. And then third component, you do del f del z. Okay. Yeah. So del f del x is just 2xy plus what is del f del y? You get x squared minus 3y squared. Del f del z, there's no z component, so you get 0. Okay, so altogether you get 2xyi plus x squared minus 3y squared. Okay, so is this a gradient vector or not? This is a function from R2 to R2. Okay, actually R3, just that the third component is 0. Yeah. Okay, so next, there's a special name we call this vector function. If the vector field is the gradient of a scalar function, then, or a scalar field, then it is called a conservative vector field. Okay, we call this kind of vector field a conservative vector field if it is a gradient of some scalar field. Okay, and on the other hand, f is called the potential function of the vector field. Okay. This one very important. Potential, very important. Yeah, in future. Very important for me. Also important for you. Okay. Which subject? Topology stuff. Symplectic topology. Yeah. Very important. Very important. In future, if you come across this, let me know. Yeah. Potential function. Not my research field, but I want to touch it. Okay. So, okay, not all the vector fields are conservative, but such fields do arise frequently in physics. Okay, for example, let F be the gravitational force field. Okay, this is a gravitational force field. You can see that this field here or function. Okay, so now you need to equivalent field to function. Whenever I talk about field, this is just a function. Okay, if it is a vector force field, this function is from where to where? Where's this vector function? F. This function f is going from where to where? F is going from where to where? R3 to R3. Why R3? Because you have I, J, and K. Okay, I, J, K, 3. This one, yeah. Yeah. Wait. Say again. Say again, sorry. Yeah. No, I mean del F could be R2 to R2. Hey, actually to R2 only because we only have two variable here. So here actually we don't need to care. So what's the problem here? What's the problem with this gradient? I mean this gradient of F and F doesn't have to have the same codomain. Yeah. Okay. I mean, this is exactly the point. So you get from so this is exactly the point just now. So you come from a scalar field, and then you obtain a vector field. Okay. In this case here, we will say that this is a conservative vector field because it is coming from a scalar field. Okay. Yeah. Not all vector field come from a scalar field, but if it comes from a scalar field, then it is conservative. Yeah, why? You got anything? Okay. Yeah. Okay. So good. Okay. So now we have this vector field. So show that F is a conservative vector field with a potential function C over square root x squared plus y squared plus x squared. Do you know how to show this? Yeah, Kyron, how to show this? Definition. What's a conservative vector field? Definition. Really of what? Not just derivative, right? It's a special one. It's a gradient. Okay, it's a gradient. Remember, derivative got directional derivative and so on. So this is the gradient. Okay, gradient of f. Okay, so you need to show that. Okay, so we want to show that f is a conservative vector field. Okay, so what does this mean? This means that f is equals to gradient of some f. Okay, for some scalar field f. Okay. Yeah, in particular here, they already give you this potential function here. Okay, they already give you the potential function. So you just need to compute whether the gradient of this potential function give you the vector field or not. Can you see that? Is it true? When you do this gradient here. So let's say we want to find del f. Okay, so what's del f here? So del little f here is del of del x with respect to del x over the square root of x squared plus y squared plus z squared. Okay, how to do this differentiation here? And then you do it for all the variables. And you do it for all variables. Do you know how to differentiate a square root function? Okay, I think Jingbo know. Hi, Jingbo. What's the first term? Jingbo, what's the negative cx? You should get 2x first, right? You get 2x, then later cancel out. Okay, you get 2x times half over x squared plus y squared plus z squared to the power 3 over 2. Okay, you can see that this formula here is symmetric with x, y, z, right? Okay, so you will get the same result by permuting x, y, z. Okay, you'll get the same result by permuting x, y, z. If I wrote in the row vector, I don't need to put this ijk anymore. Okay, because I already use comma to separate them. Okay, if you use sum, then you need to use ijk to separate them. Okay, so we got this. Then this is the gravitational field. Okay, so this is the gravitational field. Okay, so this is the gravitational field we want. Okay, minus c of, we pull the scalar out, x squared plus y squared plus z squared, 3/2. And then not quite scalar, right? Yeah, not quite scalar, but we keep this xi, xj, yj, and zk. Yeah, okay. Sometimes to be consistent, right? Okay, to be consistent, maybe you can keep one notation all the way throughout. Okay. Maybe it's not good to jump here and there. Okay, if you start with ijk, then you do ijk. If you start with a row vector, then you just do row vector. Or column vector, then you do column vector. Okay. Maybe it's not too good to jump here and there. Okay. So we have shown that del f is actually the capital F. Yeah. Is it clear or not? Is it clear? Yeah. So to show that F is a conservative vector field, you need to find a scalar field and then take the gradient. Any question before go to the next part? Next part is a new sub section. So you need to get the concept of conservative vector field right. Later we will use it in different integral. Okay. 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 Yeah. Later we'll see how useful is this conservative vector field. Okay. Next, we will go into line integrals. Okay. What's the line integrals? So to do line integrals, right? You need line first. Okay. We need a line, or we need a curve. So we start with a curve. So this curve can be defined parametrically using xt and yt. Okay. And moreover, they want it to be x prime and y prime are also continuous. Okay, so they are differentiable, and then the derivative are continuous, but not simultaneously zero on the interval AB. So they don't want to pass through the point 0, 0. Okay, origin. They don't pass through the origin. Okay. Yeah. So next, what do we do? Okay. So what do we do is here. So suppose you have a XY plane, okay, and then this is where our C live on, and this is where our C live on. Okay, so then what do we do? Actually, we want to attach a function above it. Okay, we want to attach function above it. So what do I mean here is my function is fxy. Okay, so this is actually the domain picture. Okay, this is just a domain. And then I want to do integration along this line. Last time we do along the region, right? In the assignment, you do along the double integral, you do along triangle, circle, rectangle, right? Now I don't need to along a line, a single line. Okay, so this is called line integral. So you integrate along a line. Make sense or not? Okay. Yeah. So let me see. Do I have a picture? Yeah. So let's just give you see the picture here. So let's see. This is my fxy. Okay. Along this line. So C is the line that I want to integrate. And then I integrate over this line here. So meaning I integrate along the area above this line. Okay. Sometimes we call this area a curtain or a fence. Okay. So what I wrote here is integrate over this line of my function. Okay, this will give me the area of what we call a fence or a curtain. Okay. Yeah. Okay. So I haven't tell you the definition yet, but I tell you what I'm going to do. Okay, I haven't tell you the definition yet. So what's the definition here? Okay, so this definition here is integral, right? So what's integral? Taking limit of some sum. Okay, what kind of sum you want to take and what kind of limit you are taking. Okay, so what is the sum I'm taking here? So over this curve, right? Okay, we also look at the secant. Okay, we also look at the secant. Okay, we look at the secant, and then we divide the times up to infinitely many. So we are approximating this line here. Okay, and then this length here is multiplied by the weight on the point. Okay, so how high, how tall is it? So for example here, above here, how tall? What's the weight above this line? Okay, then we will get the area or area of the curtain here. Okay, okay, yeah. So if the weight I just put 1, right, what do you get? If the weight is just 1, what do you get? If you take this secant to infinitely many, you just get a line. Okay, this is just the arc length formula. Okay, you just get a line, length, yeah, length of the line. Okay, let's see this this theorem here. So you see, you can see here, if it is 2 variable, you have this weight from the function multiplied by this part here. Remember this part? Just now we encountered this square root of sum of derivative square. Okay, so this is the length of the curve. Okay, so above this curve, we have weight. Okay, so now we incorporate the weight of the point into our integral. Okay. Yeah. So let's see. Yeah. Let's see. Okay. Let's see. So let's look at this function here. So evaluate the line integral of 2 plus x squared y dx, where c is determined by the parametric equation of half circle. Okay. And then we can also use another parametric method to calculate it. And then let's see whether they give the same answer or not. Okay, so cos t sine t from 0 to pi define a positive semicircle. X and square root 1 minus x squared also define a positive semicircle. This one, is it everyone can on the same page or not? X and square root 1 minus x squared. Everyone on the same page? Okay, so what is y squared? What is y squared plus x squared equals to 1? Is a semicircle. Okay, so if I split this y into 2 parts, plus minus square root 1 minus x squared, this actually split out the circle into positive part and the negative part. And okay, so we only take the positive part, right? Okay, because the negative square root 1 minus x squared is always negative. Okay, so it's a negative part. Okay, so let's do this line integral here. So what's this line integral equals to? Okay, so what's the formula just now we have? What's the formula we have? Okay, so how about this? This is a graph diagram or a domain diagram? Is this a graph or a domain? This is just a domain. So where's your functions lies? 2 plus x squared y. What's this function here? Function from where to where? Function from where to where? 何以 right? 何以 where's 何以 何以 Like, who is a he? Okay, yeah. So where's this function lies? 2 plus x squared y. What's this function? Function from where to where? R. How many input you need? R2 go to R. Okay, so this is a function from R2 to R. Last time what did you learn? You learn multiple integral, right? Okay, but here we only do line integral. Okay, we integrate over a line. So what's the formula here? What's the formula here? Okay, what's the formula here? Just now we have this formula. Okay, so you need to parameterize your curve into one variable using t. Okay, and then you have this extra condition here. Square root x prime t, y prime t. Okay, so what's your reparameterization here? So you have x equals to cos t and y equals to sine t. Okay, and then what else you need? You need first derivative of them, which is minus sine t for x prime and cos t for y prime. Okay, so where's your integration domain? From where to where? Where's your integration domain? Where is this line going from? This line going from where to where? 0 to pi. Okay. And then what do you need in your formula? So maybe let's copy this formula down so that we don't keep going back. Okay. So this is this, and put this formula here. Okay. Yeah. So we need to substitute our f using xt and yt. Okay. So we substitute it, become 2 plus cos t squared times sine t. Okay. Times square root of minus sine t squared plus cos t squared of dt. Okay. Altogether, what do you get? You get integrate 0 to pi of 2 plus cos square t sine t. So what's this? So how to do this integral here? How to do this integral? You can use integration by substitution. Okay, you can use integration by substitution. So the first part you got 2t. Okay, this one is easy. But the next part, what do? You can let u equals to cos t, and then du equals to minus sine t. Okay, cos squared equals to 1 minus sine square. Why change back to square again? Because we want to integrate, we only know how to integrate cos and t, right? Isn't it? So we want to change it into double integral, at double angle, I mean. Yeah. Okay, yeah, you can do that also, but let's do this since we got sine t at the side. So maybe this one is easier. So this will become what? This will become integrate of u squared minus du. Okay, so altogether we get minus u cubed over 3. Okay, which means we get cos cube t over minus 3 plus c. Okay, so altogether we get plus minus cos cube t over 3 from 0 to pi. Okay, all this thing here. Okay, So this here we will get 2 pi plus 2 over 3. Okay, 2 pi plus 2 over 3. Okay. In other words, actually we get 1 over 3 minus 1 over 3, which we get over 3. Okay. Okay. So when you do line integral with parametric equation, you should use this formula here. Okay. Remember what you need to remember is there's contribution from the first derivative. Okay. Contribution from the first derivative. Okay. Okay. Let's do one more and then we will finish today. So you see, so there's another way to parameterize this curve. So do you think that the parameterize will affect the answer or not? Does the parameterization affect the answer? Okay. Okay, let's try it out. Okay. So let's do one. Let's try it out. So the second parameterization is x equals to x. Okay. And then y equals to square root 1 minus x squared. Okay. In other words, x and y depending on x. Okay. Just now depend on t. Now depend on x. Okay. Now depend on t. Now depend on x. So what is x prime in this case? So you see, this x and this x actually is the different thing already. Okay, they are different thing. They are kind of different. Same and different. Okay, so what is x prime x? Jiawen, what is x prime x? Differentiate s with respect to x. 1. Okay. 1, 1. Okay, what is y prime x? Okay, y prime x is minus 2x over 2 times square root 1 minus x squared, which is just minus x over square root 1 minus x squared. Okay, so then we use the formula again. Okay, so let's bring this formula down. Okay, so with this formula, our line integral will change to the parametric form. Okay, so actually this formula is really important. Why is it important? Because you want to integrate over a line. Okay, what do you mean by integrate over a line? Okay, we can use definition. Okay, cutting the line into secant and then take limit. But how do you do the actual computation? So we link it back to calculus of function of one variable. Okay, because we sub everything into one variable, and then we change our domain. This domain actually live in two variable, correct or not? This live in two variable space. But how do you describe every point with two variable? Okay, I just give one variable, I can describe everything. Okay, I give you the time. Okay, I can describe everything here. How? Using the parametric curve. Okay, using the parametric curve. That's why we got this extra factor coming up here. Okay, given by the parametric curve. Okay, so let's substitute the function in. So what's our fxy again? Our fxy is 2 plus y. Yes. Okay. So 2 here is remain 2. X squared remains x squared. But y become what? Become a function in x. Okay. Which is what? Which is square root 1 minus x squared. Okay. And then there's an extra factor by the parameterization, which is square root of 1 squared plus minus x over square root 1 minus x squared squared. Yeah. And then dx. What's our AB now? What's our AB now? Okay. How to control our AB? What's the range we take for our curve? You remember? What's the range we take for our curve? -1 to 1. Okay, so -1 to 1. So we take from -1 to 1. Okay, so there's so many square root here. Okay, so let's do it. So here we got 2 plus x squared over square root 1 minus x squared. And then we square, and then we add them up. Okay, let's do it slowly. So 1 plus x squared over 1 minus x squared. Okay, so how to simplify this? You just get, what do you get? What do you get for the square root? You get square root 1 minus 1 over x. Yes. Okay, so have we simplified something already? No, not yet. Besides. Okay, so what is this? So this here is 2 over square root 1 minus x squared. How about the other term? The other term become just x squared. Okay? Okay. All right. Yeah. Okay, so how to do this integration here? I think I'll just skip it. So it will become 2 times sine inverse x. Maybe you need to do some trigo substitution. Okay, so here, but this term is easier, just x cubed over 3 from -1 to 1. Okay, so the main point here is we want to see whether they coincide or not. So maybe this step, I will say that you might want to use trigo integral. Okay, and then altogether from the first term you get 2 times power 2 plus power 2 plus 1 over 3 plus 1, which is equals to 2 pi plus 2. Okay, yeah. Okay, so it doesn't depend on your parameterization. Okay, so the key point here, what's the concept here? The concept here is the function you want to integrate over is two variable to one variable. Okay, 2 variable to 1 variable. And the domain here is a line. Line is living on the R2 plane. Okay, but how you describe every point on this line? Okay, we use a single function, which is the parametric equation. And then because using parametric equation is a function from R to R3 or Rn, so we just need one variable to control everything. So that's why this line integral here reduced to one variable case. Okay, or see this formula here. So the line integral here reduced to one variable case. Okay, but remember there's an extra factor coming from the parametric equation, which is this something looks like the Pythagoras theorem. Okay, square root of derivative squared, sum of derivative squared. Okay, yeah. Okay, before you leave, there's someone want to come and do some promotion. So please stay for work. Advertisement, sorry. Advertisement.
Hello guys. Okay, we are MIT Student Council and
use this.
okay, yeah, thanks. We are MIT Student Council and this day we have an exciting announcement to make regarding as upcoming event that we have a activities called Mystery Murder Game and which was held on 29 June and from 9 a.m. to 6 p.m. And let she introduce you all about the things. Okay, let's go.
Okay, so the upcoming event is called Murder Mystery Game, and it is on the next Thursday.
Okay, let's go.
Next Thursday, 29 June, and we will have at the block D1, and from 9 a.m. morning until 6 p.m. evening. So then the lunch is included. And we have prepared some game